In this video, we're going to take a look at 4 examples of limiting reactance problems. Limiting reactance is it's a type of stoichiometry where we determine what is going to run out first in a chemical equation, and also not just what's going to run out first, but maybe how much of something can be produced. The first question I'm going to take a look at talks about rocket engines using hydrazine and hydrogen peroxide as a propellant. It gives you the reaction, and they want to know what is a limiting reactant when you have 0.750 moles of N2H4 mixed with 0.500 moles of H2O2. Now, sometimes you'll see the problem where they give you something in grams, and if that's the case, then just convert it to moles, because the only way you can determine limiting reactants is by using the mole ratios. The very first thing you do is write down what you know. Write down what the problem tells you. So we're starting off with 0.75 moles of N2H4, and then we need to multiply it by the mole ratio because we want to know about the limiting reactant. So we have to multiply it by the mole ratio, which in this case the mole ratio is 1/1. And I do need to back up one step. You can choose either product that you want, because you're going to take both of these 0.750 and 0.500, and you're going to figure out which one makes the least amount of the same product. So I chose N2, but we could have also did a mole ratio of H2O, as long as you stay consistent throughout the problem. So the moles of N2H4 cancel, and we get 0.75 moles of N2. So that's a one-step mole ratio problem. Remember, we chose N2 the first time, so we have to use N2 the second time. The other given was 0.500 times the mole ratio is 1 to 2, because if we look at the balanced chemical equation, 2 is for H2O2. That cancels out, and we get 0.250. So in this problem, the limiting reactant is H2O2 because it produces the least amount. It's going to run out first. The other one is the excess reactant, N2H4, because we have more of it than we need. And there's all kinds of questions that can be spun off of this. I'll show you a couple of examples in the last two where they can ask you more in-depth questioning. But the most basic part of limiting reactants is do a mole ratio and figure out what the least amount is. Let's look at the second example. In this example, it's asking if 2 moles of zinc are heated with 1 mole of sulfur, identify the limiting reactant. Start off by writing what you know. There's only one possible product for this one, so that's our mole ratio. We're going to do a mole ratio of zinc sulfide to zinc. It's 8 to 8. The moles of zinc cancel, and we're left with 2 moles of zinc sulfide. The 8 to 8 reduces to 1 to 1, or you could just multiply across the top and divide by the bottom, which would be 16 divided by 8. The other one was 1 mole of sulfur, the mole ratio, and the answer is 8 moles of zinc sulfide. So if we look at this, the one that has the least is the zinc. It only has 2 moles produced, so that's our limiting reactant. And if we look at sulfur, that's our excess reactant because it produces more than we need. The third example, it's still the same type. It says that 500 moles of CO and 750 moles of H2 are present, which is the limiting reactant in the problem. So we start with 500 moles of carbon monoxide because that was given. We want to do a mole ratio problem. There's only one product to choose from, so the mole ratio is 1 to 1. The moles of carbon monoxide cancel, and we're left with 500 moles of CH3OH, which is methanol. So we have part of it done. Now we have to do the same thing with the other reactant, which was hydrogen. We're given 750 moles of hydrogen We multiply it by the same mole ratio that we used before. And this one ends up being a 1 to 2 mole ratio. The moles of hydrogen cancel, and we're left with 375 moles of methanol. So based on this problem, we can determine that the limiting reactant is hydrogen and the excess reactant is carbon monoxide. This is one of the ones I told you sometimes you have additional questions. So how many moles of the excess reactant remain unchanged? So now we're looking at, if we're given 500 moles of carbon monoxide, we know that's the excess reactant, so we know that it's not all going to be used. So in order to figure this out, we have to do another mole ratio. Start with your limiting reactant, which in this case it was 750 moles of H2, and do a one-step mole ratio from one reactant to the other. So we're going to go from hydrogen to carbon monoxide. And this would give us 375 moles because it's a 1 to 2 ratio. Now the last step you have to do, and think about that, 375 moles of the carbon monoxide react. We're given 500 in the problem, so we have to do a subtraction problem, and we do 500 moles of carbon monoxide minus 375 moles that we just said reacted would leave us with 125 moles unreacted, or it remains unchanged. That's what's going to be left over. So that's one of the ways they can ask you a more in-depth question on it. If we look at the last one that we're going to do in this video, it starts off saying 1 mole of CS2 reacts with 1 mole of O2. Identify the limiting reactant. So simple mole ratios. Again, we can pick either product in this one. I'm going to pick CO2 as long as I use it for both of them. And I get 1 mole of CO2 is produced from 1 mole of CS2. I choose the other reactant, which is O2. We have 1 mole of O2 that's given in the problem. The mole ratio is a 1 to 3 ratio. The moles of O2 cancel, and we're left with 0.33 moles of CO2. So based on that information, the one that produces the least amount is the limiting reactant, which is O2, and the CS2 is the excess reactant. We're gonna do, oh, it looks like my wife Julie is home, so don't mind the dogs barking, but I'm not gonna record this video again. So let me pause it for a second till they are done barking. Wait for it. I can't. Okay, I think we're back. Let me see. Go from. Okay, hold on. Let me get. Hey, Julie's here. Say hi.
Hi. Sorry for the interruption.
All right. Now that the craziness is gone, we were talking about right here. How many moles of the excess reactant remain? So this is just like the previous problem. So if we start with 100 moles of O2, because that's our limiting reactant, we want to do a one-step mole ratio from one reactant to the other. So we want to go from O2 to CS2, which gives us 0.33 moles of CS2. That's how much is actually used. But we're given 1 mole in the problem. So we have to do 1 mole of CS2 minus 0.33 moles of CS2, give us 0.67 moles of unreacted CS2 in the problem. So those are 4 examples that should help you out. We'll do some in class. I'll assign some for homework, and you guys will become pretty good at it. If you have any questions, stop by and see me, and we'll work it out. Thanks, and again, sorry for the interruption, but I'm sure you guys will get a good laugh out of it.